Covalent molecules. Alright, I already did ionic, now I'm doing covalent. Valent kind of sounds like valence. I don't know why, but valence, I don't know, okay. Nonmetal and a nonmetal. Covalent molecule. Okay, I know what nonmetals are. Covalent, molecule. We'll see. When a nonmetal reacts to another nonmetal, both atoms have high electronegativity. So both are good at attracting electrons. Since they both strongly attract electrons, neither element loses electrons. Instead, the electrons are shared in a covalent bond. Oh, I got a burp. Oh, yeah. Alright, whereas ionic, they were transferred. So here they're shared. Covalent bonds do not cause crystals. So I'm going to say no pattern of positive and negative, right? Because that's what a crystal was the positive, negative, positive, negative. Rather, they create small groups of atoms called molecules. So a molecule then, here I should put this, a molecule equals small group of atoms. Not a crystal, but a molecule. Orange, what was I thinking? Crazy. These are my school colors, orange and blue. My college, anyway. Alright, what are we doing? The molecules held together because the positive nucleus in each atom is attracted to the negative electrons shared between them. Right, so if we have positive nucleus, negative electron, here, these ones attract, right? But these attract too, so they're both attracting the same thing. It's like, fighting over, the chemistry notes, because there's only one set, and you both want to read the chemistry notes, and so you're both tugging on it, and so you're kind of stuck together, because, you're both fighting over the chemistry notes, which, I can give you another one. It's okay. Don't worry about it. Alright, for example, fluorine is a high electronegative atom with 7 valence electrons, so it needs one more, right? Needs octet. When two fluorines react, each fluorine atom shares one electron with the other, so both atoms achieve a full shell. I don't really get that. If they're just giving one to each other, well, okay, it's not giving, it's sharing. Together they create a fluorine molecule, F2. It's important to note that neither fluorine atom has a charge since neither gained or lost. So they're not really losing, it's like they're sharing. So it counts for both, I guess. The positive nucleus of each atom is attracted to the two electrons shared between them. The unshared pairs of electrons are called lone pairs. Okay, I should define that too. So unshared pairs equal lone pairs, like loner, I guess. The fluorine molecule contains a total of 6 lone pairs. So here's the fluorine. There's 7 valence electrons, and now they share. So I guess there's 8 and 8, but they haven't actually lost or gained. They're in the middle. They're tug-of-warring it over it. So this would be the unshared pair. Or all these, really. These would all be the unshared pairs. The lone pairs. So this one would be, this pair right here is the shared one. Now there's just lines everywhere. That was a poor annotation decision. Okay, this is 2 H's. Oh, that's water. Looks like Mickey Mouse. So this also looks like these are shared, and these are shared. So hydrogen's sharing 1, oxygen's sharing 1 there, so oxygen's sharing 2, but they've all got a full outer shell. Although hydrogen doesn't have 8, so it's not really an octet. It's like a dual or a duet or something. Another example is a water molecule. Both hydrogen atoms have 1 valence electron, while the oxygen atom has 6 valence electrons. When they share electrons, hydrogen achieves a full shell of 2 electrons. Right, so it's not really an octet, it's like 2. While oxygen achieves a full shell of 8 electrons. Since both hydrogen and oxygen atoms share electrons, the atoms are tightly bound together in a covalent bond, but the atoms do not become ions. Do not become ions. So if we go back to the water then, this is neutral. And I guess the fluorine's neutral too. Neutral. Because they're just sharing. The elements hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine form covalent bonds with themselves because they have such high electronegativities that they cannot exist as single atoms in nature. So all these ones, if I just say oxygen, I'm actually talking about O2, I guess. They look like butts. There's actually an interesting way to remember this. It's oh, I shouldn't teach you that one. What the heck. It's have no fear of ice cold beer. See, H, hydrogen, nitrogen, fluorine, oxygen, I, Cl, Br, chlorine, bromine. So have no fear of ice cold beer. So if that helps you remember it. Or the high school appropriate one is Hofbrinkel. Oh, that's not an E, that's a F. Hofbrinkel. I don't really know what a Hofbrinkel is. It sounds like maybe it's from Harry Potter or something, but people remember it for some reason. Hofbrinkel sticks in your head. Okay, so these ones, if I just say hydrogen, I don't mean H, I mean H2. So you gotta memorize those. Naming covalent compounds is a little more complicated than ionic compounds because there are no charges to use to determine the formulas. Prefixes are used, so prefix, pre goes before, are used to indicate how many of each atom there is. A prefix is always used except for the first atom if there's only one in the molecule. So prefixes for naming, mono, di, tri, like tricycle, tetris, pentagram, hexagram. Okay, I get it. Examples, dihydrogen monoxide. So there's two hydrogen, di, and there's mono, one oxygen, so monoxide. Here, oxygen difluoride. So here, it's the first one, so we don't need mono-oxygen. It's just oxygen difluoride. And here, P2O4, well, the 2 would be, and the 4 would be, and then we'd have ide. You give it a shot. Come on, you can do it. Okay, after you're done with that, go to this reading, which I forget which page it is. You can figure it out, though. Here we go. So, Lewis structures with multiple bonds. In class, we'll talk about how to do them with single bonds, but you'll kind of figure it out from this, I think. So in certain molecules, some atoms must share more than one pair of electrons. If an atom shares more than one pair of electrons, it forms either a double, so that would be 2, or triple, that would be 3, bond. The types of bonds are summarized in the table below. So here, single, 1 dash, doubles 2, triples 3. So here, nitrogen, in order to get an octet, it has to actually share 3 pairs with itself. Remember, this is a product of Hofbrinkel. They're very electronegative. They do this naturally. So this is actually 3 pairs, which is 6 electrons for nitrogen. So let's look at these examples. So for example, the oxygen atoms in an oxygen molecule must share 2 pairs or 4 total electrons. The oxygen makes a double bond. So each oxygen has to make 2 bonds. There's only one atom to make a bond with, so it makes 2 with the other oxygen. So typically, you would see this like this. But sometimes people join the lone pairs together just because it's quicker. But typically this is how you would see it. And then nitrogen does the same thing, except it has to share 3 pairs. So it looks like this. So triple bond, double bond. Alright. So more Lewis structures illustrating double and triple bonds. Examine each structure carefully. Circle the electrons shared by each atom to verify that every atom has a full shell. Okie doke. Label each double and triple bond. Okie doke. So it says circle the atoms shared by each atom. So this would be oxygen, right? Here's the other oxygen. And then here's the carbon. There's 2, 4, 6, 8. Who do we appreciate? Mr. Larkin? No. Well, yes, of course. So each bond counts as 2, remember? So that's 8, 8, 8. So that's good. Here, hydrogen just has, the 2. Oops. But it only needs 2, right? Whereas this carbon here needs 8, which it actually does have, because 2, 4, 6, 8. Same thing with this carbon. And then the bromine here has 2, 4, 6, 8, so it's good too. So everything has a full shell. What about this? Hydrogen has 2. This carbon has 2, 4, 6, 8. This carbon has 2, 4, 6, 8. And this iodine has 2, 4, 6, 8. So everything's good. So now label double and triple bonds. So these ones are double, 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 toil and trouble. Have you read Macbeth? No? This is a double as well. And then this one is a triple. Interesting. Okie dokie. Yay, Lewis structures.